Now we want to look at what happens when we have polar coordinates for our regions in the plane. So of course we can just think of polar coordinates as exchanging x and y for two different variables, r and theta, and they're related this way. Or you could relate them the other way around by saying r squared is x squared plus y squared, and the tangent of theta is y over x. Now the point of doing this is that some things are much easier to express in polar coordinates than they are in the rectangular coordinates x and y. So for example, if we have the inside of this circle of radius b, this disk here, we can write that as r goes from 0 to b, and theta goes from 0 to 2 pi. Or if we have a pi wedge, okay, which is b on the straight sides, and whose angles go from theta 1 to theta 2, we can write that as r goes between 0 and b, and then theta is between these two angles, theta 1 and theta 2. Or if we have this ring shape, then that's r going between a and b, and theta 1 going all the way around, or theta going all the way around. And then if we have a section of a ring, we combine all these different possibilities. R goes between two numbers, and theta goes between two numbers. And if you think about it, what it means is we have both variables r and theta have constant bounds, which means that in r theta, they're all rectangles. Right, so they're not actually rectangles when you draw them in the plane, but in terms of the r and the theta variables, they both have constant bounds, which makes it really easy to do a double integral with them. And then you get some crazier things, like you get one of these curves expressed in polar terms. So this one is r equals cosine of 2 theta. And theta goes between theta 1 and theta 2 to give you one of these leaves. Okay, so in that case, we would have that the bound on r does depend on theta. So it's a little bit more complicated, but still way easier to do this way than it would be with an x and a y.